All right, well, thanks again for joining us, everyone. I'm Amy Guerin, the Director of Brand and Digital Strategy with AOCS, and I'm here with Dr. Emily Tan. And Dr. Tan is the Head of Applied Research at KLK Oleo in Malaysia. She holds a master's and doctorate degree in chemistry from the University of Bristol in the United Kingdom and completed a postdoctoral fellowship at the University of Wisconsin-Madison in the United States. Following her postdoc, she joined KLK Oleo, where she has held various positions at one of the world's largest oleochemical manufacturers. Their products are applied in many different industries, including home care, personal care, and functional foods. Currently, Emily also holds the appointed role of Director of Industrial Linkages for the Malaysian chapter of the American Chemical Society. And Emily originally presented this research at the 2021 AOCS Annual Meeting as an ePoster. And just in a moment, I'll drop a link to that ePoster into the chat so that you have access should you want to look at that as well. We will answer questions after the presentation. So any questions that you have, please drop those into the question area on your webinar control panel, and Dr. Tan will address those at the end of the presentation. So with that, we will get started, and I have to grab back presenter control from you, Dr. Tan. Okay, now there we go. So with that, we will begin the presentation.
This webinar is entitled Oil Drop Deposition and Rheology of Methyl Ester Sulphonate-based Surfactant Systems for Hair Shampoo Applications. In hair care, the primary function of a shampoo is to remove excess oil and sebum, pollution from the environment, and residues from hairstyling products. Therefore, the most important ingredient in shampoos are surfactants. Surfactants emulsify these unwanted materials and pull them into water so that they can be easily washed away during rinsing. After using a shampoo, we would normally use a conditioner. The primary function of a conditioner is to deposit conditioning agents on the hair fibers. The conditioning agents form a protective lubricant layer on top of the hair fibers, and this reduces the surface friction between the individual hair fibers. The observed effects are the hair will feel smoother and softer. Because the hair is smoother and softer, it is less likely to get tangled and less force is required to comb. If it's easier to comb, then the individual hair fibers are more likely to be aligned. Aligned surfaces reflect light better, so the hair will also look shinier. The importance of using a conditioner can be seen in this example taken from a textbook. On the left, the hair fibers were washed with shampoo only and then combed 700 times while wet. Without the protective layer of the conditioning agents, the cuticles became raised, chipped, and torn away. On the right, the hair fibers were washed with a conditioning shampoo and then combed 700 times while wet. The layer of conditioning agent protects the cuticles and minimal damage was observed. Conditioning shampoos were introduced to the global market in the 1980s. They combined the functions of a shampoo and a conditioner. Consumers can save time by doing one step instead of two in the shower, and they can save money by buying one product instead of two. Nowadays, most shampoo products are actually conditioning shampoos. Looking at the number of new shampoo products launched in the past 5 years, more than 30% of them claim to be moisturizing or hydrating. So these are definitely conditioning shampoos. The remaining new shampoo products do not make these claims, but 96% of them list conditioning agents amongst their ingredients, and therefore they are technically conditioning shampoo. A lot of shampoo producers include conditioning agents into their product because most consumers these days expect even normal shampoos to have at least a little bit of conditioning effect. Depending on what the shampoo producers would like to claim and the consumers that they are targeting, the shampoo producers would vary the amount of conditioning agents that their shampoo deposits on the hair and therefore the conditioning effect experienced by the consumer. Shampoo producers cannot prepare conditioning shampoos by just combining surfactants and conditioning agents. If they did so, only a very minute amount of the conditioning agents, or none at all, would have been deposited on the hair. This is because most surfactants used in shampoos are anionic surfactants to deliver good cleansing performance. They absorb onto the surface of the conditioning agent droplets and render them negatively charged. The surface of hair is also negatively charged, and the electrostatic repulsion between them will prevent the deposition of the conditioning agents. To overcome this, formulators add cationic polymers as a mediator. The anionic surfactants and the cationic polymers absorb onto the surface of the conditioning agent droplets. Because the concentration of the surfactants is significantly more than the polymers in the conditioning shampoo when it's in the bottle, the overall surface charge on the droplet is still negative. However, when the shampoo is applied on the hair and water is added during rinsing, the surfactants are washed away more easily compared to the hydrophobic polymers and conditioning agents. The overall surface charge on the droplets would become positive as more surfactants are washed away. Now there is electrostatic attraction between the droplets and the hair fibers, and deposition of the conditioning agent occurs. The amount of conditioning agents deposited on the hair depends greatly on the complex interaction between the surfactants, polymer, conditioning agents, and hair fibers. Interactions including electrostatic, hydrophobic, and polymer bridging surface forces. The right combination of interactions will increase the amount of conditioning agents deposited, and the consumer will experience more conditioning effect. We were interested to compare the effect of using different surfactant systems on the amount of conditioning agents deposited. To conduct this study, we used the press drop method, which evaluates the adhesion of an ore drop to a substrate. A drop shape analyzer was upgraded with a piezo-driven membrane for precise control of the ore drop volume. A drop of the conditioning agent, which we will call the ore drop, was formed at the tip of a metal capillary that was submerged in a surfactant and polymer mixture. To mimic the surface of hair, we treated a hydrophilic microscope glass slide with HMDS to form a hydrophobic surface with a measured contact angle of 88 degrees. For comparison, virgin hair has a contact angle of about 100 degrees, while chemically damaged hair is about 70 degrees. At the beginning of the experiment, the ore drop was pressed against the substrate by increasing its volume. It was left in contact with the substrate for several minutes. Then the ore drop was slowly detached from the substrate by reducing its volume. The shape of the ore drop during detachment was recorded using a camera. The detachment was repeated several times to ensure that the results were reproducible. Then the surfactant and polymer mixture were diluted by replacing a portion of the mixture with water, and another detachment study was conducted. By using this stepwise dilution, we were able to study many different concentrations very quickly and repeat whole sets of experiments to ensure that the results were reproducible. Here are some images of ore drops during detachment. At 0 seconds, the ore drop is still pressed against the substrate. We started the timer and slowly detached the oil drop from the substrate by reducing its volume. In the first set of pictures, the dynamic contact angle between the drop mixture and substrate remained close to zero during detachment. This shows that the oil drop is not adhering to the substrate, and therefore we label this as a non-adherent drop. In the second set of pictures, the dynamic contact angle increases significantly during detachment. This is because the oil drop is adhering to the substrate, and therefore we label this as an adherent drop. We observe non-adherent drops at high surfactant concentrations because anionic surfactants suppress oil drop deposition. At lower surfactant concentrations, when more surfactants are washed away during rinsing, the oil drop begins to adhere to the substrate. The highest surfactant concentration, at which the oil drop begins to adhere onto the substrate, is called the threshold concentration for drop adhesion. For brevity, in this presentation, we will call this the adhesion concentration. A higher adhesion concentration is preferred. In the initial stages of rinsing, the surfactants, conditioning agents, and polymers are washed away with water. This is because the conditioning agents are not adhering to the hair. Surfactants are washed away quicker because they are more hydrophilic. When the surfactant concentration drops to the adhesion concentration, the conditioning agents begin to adhere to the hair. Hence, a higher adhesion concentration means that less conditioning agents are washed away, more conditioning agents are deposited on the hair, and the consumer will experience more conditioning effect. Using this technique, we studied a few surfactant systems. For example, this is a binary surfactant system with an anionic and a zwitterionic surfactant. The anionic surfactant is a methyl ester sulphonate with a C14 carbon chain length. MES C14 provides good cleansing performance. The zwitterionic surfactant is cocamidopropylbutane, CAPB. This is a very popular surfactant for hair shampoos. It is usually used as a secondary surfactant rather than the primary surfactant. This is because it provides moderate cleansing performance only. CAPB is usually added to improve foam performance and to adjust the rheology of the shampoo. The total surfactant concentration was fixed at 6 weight %. The ratio of MES to CAPB was varied from 0 weight fraction of CAPB to 1. At 0 weight fraction of CAPB, the mixture contains MES and no CAPB, while at 1 weight fraction of CAPB, the mixture contains CAPB and no MES. In all of the experiments conducted, Jaguar C13S was added as the cationic polymer. Its initial concentration was fixed at 0.1 weight %. For the conditioning agent, we used polydimethylsiloxane. Both of these ingredients, the Jaguar and the siloxane, are widely used in hair shampoo products. Our experimental results showed that the adhesion concentration decreases with increasing weight fraction of CAPB. This means that higher ratios of CAPB suppresses oil drop deposition. We propose that this is due to the binding energies between CAPB and polymers is stronger than between MES and polymers. This means that CAPB will stick more strongly with the polymer, making it difficult to wash away CAPB during rinsing. CAPB continues to suppress oil drop deposition until sufficient CAPB has been washed away. Besides MES C14, we also studied MES C16, which has a slightly longer hydrophobic carbon chain. The studies were conducted using the same experimental conditions. The results showed that increasing weight fraction of CAPB also suppressed the adhesion concentration of the surfactant system. More importantly, we observed that the adhesion concentrations for MES C16 was consistently higher than MES C14 by almost a factor of 2. This suggests that more conditioning agents would have been deposited on the hair if MESC16 was used as the primary surfactant instead of MESC14. As the only difference between these molecules is their length of carbon chain, we propose that the hydrophobic tail may have helped mediate the adsorption of the polymer to the substrate, so less of the surfactants has to be washed away before drop adhesion occurred. Next, we compared the MES-based surfactant systems with sodium lauryl ethyl sulphate. SLES is a very popular surfactant for hair shampoos. It's listed as an ingredient in more than 60% of the new shampoo products launched in the past 5 years. Using the same experimental conditions, we observed that the adhesion concentrations for SLES are lower than MESC14 by a factor of 2 and lower than MESC16 by a factor of 5. All drop adhesion is easier using MES as the primary surfactant compared with SLES. We propose that this is due to the different specific binding energies of the sulphonate and the sulphate functional groups. We have also repeated these studies with the hydrophobic glass substrate replaced with an untreated hydrophilic glass. As mentioned earlier, the untreated hydrophilic glass has a contact angle of 23 degrees. This is significantly lower than chemically damaged hair, and therefore this is a rather extreme scenario. The observed adhesion concentrations for all surfactant systems were significantly lower, suggesting that it's more difficult to deposit conditioning agent on chemically damaged hair compared with healthy hair. Meanwhile, the trend of MESC16 performing better than MESC14, which performs better than SLES, remained the same. Taking the MESC16-based surfactant system, because it yielded the highest adhesion concentrations, we next look at the effect of adding rheology modifiers on the amount of oil drop deposition. This is because most shampoos will contain some rheology modifiers, and we will talk about rheology in the second part of this presentation. In this slide, we were interested to investigate the effect of adding a small amount of two very common rheology modifiers, sodium chloride and CMEA. We observed that the addition of sodium chloride increased the adhesion concentrations. We propose that the sodium chloride enhances the segment-segment attraction of the hydrocarbon chains in water due to sorting out effect and screening of the electrostatic double-layer repulsion. Meanwhile, addition of CMEA decreased the adhesion concentrations. We propose that CMEA binds to the hydrocarbon chains and renders them more hydrophilic, thus suppressing segment-segment hydrophobic attraction and effect of polymer bridging. So formulators can consider using sodium chloride instead of CMEA to modify the rheology profile of MES-based surfactant system, as sodium chloride can enhance oil drop deposition, while MEA had the opposite effect. We have also conducted some comparative experiments using human hair. The conditioning agent, polydimethylsiloxane, was spiked with a fluorescent dye. The hair fibers were soaked in this conditioning agent before it was immersed in a solution of surfactants and cationic polymers. The initial solution contains 6 weight% of the surfactant and 0.1 weight% of the cationic polymer. In subsequent experiments, solutions were prepared with increasing dilutions. The hair fibers were visualized using a fluorescent microscope. At high concentrations of MES and SLES, no oil drop deposition was observed on the hair fibers. At 6 times dilution, some oil drop deposition was observed for the MES solution. However, for SLES, no deposition was observed at 6 or 12 times dilution. At 24 times dilution, a small amount of deposition was observed. The amount of deposition increased notably at 96 times dilution. Based on this study, the adhesion concentration of MESC16 is 4 times higher than SLES. This is consistent with previous studies using the press drop method. Additionally, In this study, we can see that for MES, the oil drops are small and spread across the hair fiber, while for SLES, the oil drops are large and spaced far apart. This suggests that MES provides a more uniform layer of conditioning agents across the hair compared with SLES. To summarize the first part of our presentation, adhesion concentrations were measured using the press drop method and by visualizing on a human hair using fluorescent microscope. Higher adhesion concentrations means more oil drop deposition. MES-based surfactant systems provide more oil drop deposition than SLES-based surfactant system. Although Cat B is often used as a secondary surfactant in hair shampoo, it is actually detrimental towards oil drop deposition for MES and SLES-based surfactant systems. In terms of rheology modifiers, CMEA suppresses oil drop deposition, while sodium chloride enhances oil drop deposition. Sodium chloride is significantly cheaper than CMEA. By using MES with sodium chloride, formulators can achieve two things at the same time. They can deliver more conditioning effect while reducing the overall cost of the formulation. Our second topic for today's presentation is rheology. While oil drop deposition is important for delivering more conditioning effect, the rheology profile of a shampoo is important because it's linked with consumer sensory evaluation. For example, how it feels on the palm and how easy is it to spread across the hair. Different formulators may desire shampoos with different rheology profiles. The aim of our next study is to evaluate how easy is it to modify the rheology profile of MES-based surfactant systems. Rheology studies were conducted using a rotational rheometer with a cone and plate geometry at 25 degrees. The apparent viscosities at different shear rates were obtained. At low shear rates, the viscosity does not change significantly with increasing force applied. At this plateau, the system is exhibiting Newtonian behavior. At high shear rates, the viscosity drops significantly with increasing force applied. The system is undergoing shear thinning. This is a non-Newtonian behavior. This rheology profile is suitable for shampoos. Because we want it to be fairly viscous when it's on our palm, we do not want it to be so runny that it spills onto the floor. But at the same time, we want it to be flowable when we squeeze it from the bottle and when we spread it on our hair. Different formulators will have different requirements for the length of the plateau. For example, formulators for children shampoo may want to have a longer plateau because children are still learning how to hold things, and parents are more likely to buy products that do not spill off their hands easily. Whereas formulators for adult shampoo, targeted towards convenience, may want a shorter plateau so that the product is easily flowable and easy to spread on the hair. Formulators may also desire a higher initial viscosity for these products because consumers often link shampoos that look more viscous as being more premium and concentrated. This initial viscosity of the plateau is called the zero shear viscosity, and we investigated how this viscosity can be varied. In the graph on the left, the zero shear viscosity obtained was plotted against the total surfactant concentration. Using MES C16 alone, the zero shear viscosity increased slightly with increasing MES concentration. The viscosity can be increased more rapidly by increasing the weight ratio of Cat B. Our previous study showed that the addition of sodium chloride can enhance oil drop deposition. Sodium chloride is usually used as a rheology modifier, and hence in the graph on the right, we were interested to see how sodium chloride affects the viscosity of MES alone and MES with a small amount of Cat B. In both cases, a typical salt curve with high viscosity maximums were obtained. Most hair shampoos have zero shear viscosities that are significantly lower than 200 Pascal seconds. Hence, formulators do not have to add Cat B to reach their target zero shear viscosity. They could use just MES and sodium chloride. Sodium chloride is also cheaper than Cat B. By using just MES and sodium chloride, formulators can achieve three things at the same time. They can deliver more conditioning effect, achieve their target zero shear viscosity, and reduce the overall cost of the formulation. To summarize the second part of our presentation, the rheology profile of MES-based surfactant systems can be easily modified by varying the total surfactant concentration, ratio of Cat B, or addition of sodium chloride. Having shown that MES is a promising new primary surfactant for conditioning hair shampoos, we will next like to talk about MES itself. Here are some key benefits of MES. We have shown in this presentation that it can enhance oil drop deposition. Its rheology profile can also be easily modified to suit the customer's preference. Both of these benefits can be further enhanced using sodium chloride, a very cost-effective ingredient. In addition to these benefits, MES is produced from vegetable oils, which is a natural, renewable, and sustainable resource. Because of this, MES has a high natural origin index. The vegetable oils are trans-esterified and sulphonated to form MES. The MES molecule is made up of three parts: a fatty acid carbon chain, a methyl functional group, and a sulphonate functional group. It does not contain any ethylene oxide functional groups, and therefore MES is EO-free. Because it's EO-free, there is no possibility for 1,4-dioxins to be formed during the manufacturing process. 1,4-dioxin is a potential human carcinogen, and some government regulatory agencies have specified the maximum limit of dioxin that can be present in home and personal care products. Many of these agencies are keen to reduce this maximum limit even further. Formulators will have to start sourcing for suppliers that are capable of producing surfactants such as SLES with lower dioxin contents. Or formulators can consider replacing their current surfactants with surfactants like MES that does not contain any dioxin at all, and thus completely eliminate this issue for the future. MES is sulfate-free. It does not have a sulfate functional group. There's a trend amongst consumers to move towards sulfate-free products. Sulfate-based surfactants such as SLES and SLES, sodium lauryl sulfate, are the most popular and conventional primary surfactants for hair shampoos. However, there's a lot of negative press about these surfactants. One of the consumers' concerns are that these surfactants may be causing too much skin and eye irritation. We have tested the irritancy potential for MES and found it to be mild to skin. The in vitro experiments were conducted in the UK using a reconstructed human epidermis called epiderm. A 5% MES solution was applied on epiderm. After selected exposure durations, the tissue viability of the epiderm was evaluated, and the time taken for tissue viability to drop by 50%, the ET50, was determined. The results for 5% MES was compared with their standard benchmark chemicals, and MES was classified as mild. It is significantly milder than SLS. The ET50 for a 1% SLS solution is less than 5 hours. In contrast, the ET50 for MES is more than 10 hours, double the duration, even though the concentration used is 5 times higher. This is a visual comparison of MES with other surfactants used in hair shampoos. The most popular are the sulfate-based surfactants, SLES and SLS. Compared with SLES, MES has a higher natural origin index. The natural origin index is based on the ISO 16128 standard. A value of 0 means that the product is completely from fossil fuel origin, whereas a value of 1 means that the product is completely from natural origin. SLS has a higher natural origin index compared to MES. However, it also causes significantly more skin irritation. As consumers move towards sulfate-free products, hair shampoo producers are slowly replacing SLES and SLS with other surfactants. Most of these surfactants have a lower natural origin index compared with MES. The main exceptions are alkyl polyglucosides, APG, and amino acid surfactants, AAS. APG and AAS are gaining popularity amongst consumers due to their high natural origin index. However, it is difficult to modify the rheology profile of these surfactant systems. Formulators have to add secondary surfactants like CAP-B, CDA, and CMA to help adjust the rheology profile. These secondary surfactants have a lower natural origin index compared with APG and AAS, and therefore they will lower the overall natural origin index of the formulation. In addition, APG and AAS are very expensive surfactants. They can range from being 2 to 15 times more expensive than SLES and SLS. In contrast, MES is much cheaper. It's even cheaper than SLES and SLS. To summarize, MES provides a good balance between performance and the natural origin index. Hair shampoo manufacturers can also optimize the formulation cost. AOCS Oleo produces 3 types of MES product under the sulphonate brand name: flakes at 90% active, powder at 80% active and with 10% zeolite, and paste at 30% active. We produce MES in different forms to tailor according to our customers' application needs, as well as to suit their production process. For example, solid products such as Syndet and dishwashing tablet are usually produced using solid raw materials. Some manufacturing plants have the capability of grinding flakes into powder, while others might prefer to skip this step and directly purchase the powder. Meanwhile, for liquid products such as hair shampoo and laundry liquid, MES in flake or paste form would be more suitable. Some manufacturing plants have the capability of dissolving flakes in heated water, while others might prefer to skip this step and directly purchase the paste. Besides MES, AOCS Oleo produces a wide spectrum of products, from basic oleochemicals to derivatives, specialty, and fine chemicals. Our products are used in a diverse range of applications. For example, they are used as ingredients in a variety of personal care and home care products, and as additives in food products. We have a total of 15 manufacturing sites in 7 different countries, and we supply to more than 120 countries. AOCS Oleo is part of the manufacturing segment for AOCS. Besides this segment, we also have a property development segment and a plantation segment. The plantation segment is the oldest. The first company was started in 1906, and therefore we have been in operation for 115 years. Before I close, I'd like to thank the many people that have contributed towards the work in this presentation. Professor Peter, Professor Krashimir, their research team, as well as my colleagues at AOCS. If you would like further information, please send me an email or drop me a message on LinkedIn. You can also visit our company website to find more information about our products.
Hey, thank you, Dr. Tan. That was a very interesting presentation. For those in the audience, if you would have any questions, you can drop those into the question box, and Dr. Tan will be happy to answer those for you. While we wait to see if any of those questions come in, I was going to ask you, just because I happen to have very hard water, is how well does MES work in that situation?
So MES actually performs very well with hard water. It has good hard water tolerance. It's another key benefit for MES. Due to the methyl ester functional group, it's quite bulky, so it prevents the calcium and magnesium ions from binding to two different surfactants and precipitating out. So MES has good hard water tolerance. It would do well in your area.
Thank you. Interesting, yeah. I learned something new with all of these. So I'm not yet seeing any questions from the audience. Just to give them another moment, everyone that's attended, you will receive a link to the recording, and that'll go out tomorrow, as well as a certificate of attendance, and they'll all be in one email. And Dr. Tan has provided her email address, so should you have questions after you've had time to kind of digest everything, you can definitely get in touch with her via email as well with questions. So thank you everyone so much for attending, and thank you Dr. Tan for presenting at both the annual meeting as well as joining us for this AOCS webinar.
Thank you for having me.
Hope everybody has a great day. Take care.